All right. Hello, everyone. Welcome back. Reese here, along with my cat, Bet. She's going to be hanging out with us. If you get stressed out, pause the video and look at her. She's so cute. She's my stress relief. But we're going to hop on to part 2 of discussion number 1. So I'm going to get my screen share going and we are going to get on into it. So let me hop on over. All right, let's see. Unable to connect. All right, there we go. Awesome. So question number 2, what we're kind of looking at are some different ions, the direction they'll be either absorbed or secreted, and the different transporters that will allow that to happen. In this column right here, we're kind of having some goals and oops, my other cat just ran into the wall. So this will be our goals and these will be the methods we use to complete them. So I redrew this diagram right here so we could have a little bit extra room, and I recommend you kind of drawing it out too, just because that space isn't really enough for this problem. But let's hop on into it. So I kind of broke this down into a 2/3 step problem. So step number 1 is going to be to draw out our concentrations. So draw out those concentration gradients. And whenever you set up your problems like this, it really helps you answer the word problems that follow it. So I think drawing out these problems gives you this good visual idea on how to answer the more wordy problems. So first, again, we're going to draw out those concentration gradients. So let me move over to, let's see, what color am I going to use? I'll use, I'm so picky about my colors. We're going to use this color blue. All right, awesome. So here, actually, you know what? I'm sorry, I changed my, you know what, whatever. I need to stick with this color. This is what we're gonna use. So here we have our sodium ion, and we will draw that out across this cell. So sodium, sodium, sodium. And one thing I've repeated many, many times is sodium is always going to be higher outside of the cell. So it's always going to be in higher concentrations outside of the cell, lower concentrations inside. You can see here, Dr. Chang kind of put that typical ICF versus ECF concentration, meaning he wants you to know that it is typical that sodium is always going to be higher outside of the cell. However, with our hydrogen, he gave us the concentration method. So he told us. And when he tells us that hydrogen is going to be high in the lumen, that means it's going to be low everywhere else because he directly specified that it is going to be high in the lumen. That means it's going to be low everywhere else. And then lastly, we have our bicarbonate, or HCO3, and Dr. Chang specified that it is going to be high inside of the cell. So that means it's going to be low everywhere else. So high inside of the cell because Dr. Chang specified that, and low everywhere else. All right, awesome. So we have now completed step number 1 of drawing out those concentration gradients. So we're going to move to step number 2. Step number 2, we're going to kind of draw out our secretion and absorption goals. So we're going to kind of draw out those secretion and absorption goals. So I am going to represent absorption with an arrow going to the I'm bad with left and rights, going that way. So going that way on my screen, that's going to be our absorption area. And that would make sense because it's showing us moving from the lumen over to the extracellular fluid. So moving into the body, being absorbed from the outside. Remember, when we say lumen, we're typically talking about outside of the body. Extracellular fluid, we're talking about inside of the body. So we're going to be absorbing. And given in the question, we can see that sodium and bicarbonate are both going to be absorbed. So we're going to draw sodium and bicarbonate on the end of this arrow. Now we have to draw our other goal, which is going to be secretion. So this is going to be our secretion line because that is showing something leaving the body, exiting the extracellular fluid and moving out into the lumen. And we can see here that hydrogen is going to be secreted, that is given. So with this kind of rough idea, with this rough diagram, now we can finally look at the transporters and figure out which side, whether it's going to be the luminal side or the extracellular fluid side, they will take place. So let's hop into the first, or well, honestly, I can just give you a tip first. You're always going to want to kind of knock these out by first hitting any type of transporter that deals with facilitated diffusion, just because that's easiest. So the first one we're going to look for is any type of transporter that deals with facilitated diffusion, just because that's easy and simple. So we know that a sodium channel is a type of facilitated diffusion. A basic channel is going to be that facilitated diffusion. So we can represent that with light purple. So we'll look at the sodium channel. So what we're going to do is, and just a little hint, we're only going to be using one of each of these. So we cannot draw them on both sides. They will be on one side or the other. But what I'm going to do is I'm going to draw up two, and I'm going to kind of leave it up to you to decide. I'm going to let you work it out in your head, and then I'll give you the answer. So I don't know if you want to draw this out as I'm going along or wait until the end, just because we will be erasing. You can use X's if you would like. But hopping on in, let's go ahead and draw out two possible scenarios for this sodium channel. So we have sodium out here on the outside. If it's facilitated diffusion, that means it's going to be moving with its concentration gradient. So facilitated diffusion, moving from an area of high concentration to low. But again, we can only use each of these transporters one time. So with that information, I want you to sit here and think which side is going to be the correct movement. Which one of these is going to be the correct movement? After you've thought it through a little bit, I'm going to tell you that the incorrect one would be this side. And can you think of why? I'll tell you now, because we want to follow our arrows. So down there, I have that sodium is going to be absorbed. So these arrows, we always want it to be following. We always want it to follow the arrows. So if sodium's being absorbed, it needs to be moving that way. So this one is not correct. So we're going to go ahead and erase it. So that's channel number one. So the second type of channel or transporter that I would recommend completing just for simplicity and ease would be any type of primary active transport channel, or sorry, I keep saying channel, transporter. So any type of transporter that's dealing with primary active transport. And if you don't know what that is, that just means any type of transporter that's going to be going through ATP hydrolysis, pretty much just meaning any type of transporter that's going to be using ATP. So words we can look for here are ATP, of course. So as you can see, we have some type of transporter called the sodium potassium ATPase transporter. So let's go ahead and label it on our cell. So let's see. Here we will label it, and we will label it on this side as well. So we have sodium coming in. However, whenever sodium comes in, potassium comes out. And I am sorry, let me pause this. I realized I made a mistake. Okay, I am totally sorry about that. So we're gonna go ahead and erase something. So whenever we're talking about primary active transport, we need that ATP because we're moving against the concentration gradient. So primary active transport is using that ATP hydrolysis so it can move against its concentration gradient. So I messed up my arrows on that previous example. So what's actually going to be happening is that sodium is going to be moving out of the cell and potassium will naturally move inside of the cell. That means potassium will be following its concentration gradient, giving off some ATP so that sodium can move against its concentration gradient. Same thing on this side, since it's primary active transport requiring that ATP, ATPase, that sodium will again be moving against its concentration gradient from an area of low to high. And it is able to do that from the ATP or energy given off by potassium moving from high to low with its concentration gradient. So again, I want you to take a second to kind of work out in your head which one of these is correct. Will it be on the luminal side or will it be on the extracellular fluid side? So go ahead and think it through in your brain. And now I will go ahead and tell you. The incorrect side is going to be this one. Again, because sodium needs to be moving in the absorption direction. It needs to be absorbed by the body. We're not trying to secrete sodium, we're trying to absorb it. So it's going to be on the extracellular fluid side. So now I'm going to erase this just so it looks a little more clean. All right, so after knocking out our facilitated diffusion transporter and our primary active transporter, next I would recommend looking for that secondary active transporter. So whenever we talk about that, and give me one more second. Excuse me. So now we're going to be looking for our secondary active transporters. And the key word that we will look for when we're looking for those secondary active transporters are the word co-transporters. So co-transporters are going to denote that it is a secondary form of active transport. So we can see that we have two different forms of co-transporters here. And I will tell you that co-transporter is a general term describing either a symport or an antiport. A symport means that those two molecules will be moving in the same direction, and an antiport means they're going to be moving in opposite directions. So we can begin either with the sodium hydrogen co-transporter or the sodium bicarbonate co-transporter. So sorry about that. And I would choose to start with the sodium bicarbonate co-transporter because we can see that that's going to be a symport. It's going to be moving in the same direction. So that symport means they're going to be moving in the same direction. Those are just a little bit easier to solve first. So now we can draw out, and let me clear this up just a little bit more. Now we can draw out that sodium bicarbonate transporter on each side to decide which one we're going to believe it is or decide on what it is. So a co-transporter, and we decided it's a symport because they're both moving in that direction. That means our arrows will be going this way. So our sodium will be coming in and our bicarbonate will be coming in. Same thing on this side, symports move in the same direction, and we know we want to move them in the absorption direction due to our arrows. We can draw it here on this side as well. So now that we've drawn it on both sides, take a second to think to yourself, is it going to be on the luminal side or will it be on the extracellular fluid side? Now I'll tell you which one is incorrect again, and the incorrect one will be this one, because remember, our overall goal is to absorb that sodium and bicarbonate into the body. If we just absorb it from the lumen to the epithelial cell, it has not been fully absorbed by the body, and that is not our goal. We want our body to absorb that those two molecules, so this would be the incorrect side, and the correct side would be that extracellular fluid side. Nice. So now we're left with one more, and that is our sodium hydrogen co-transporter. And we can see here that those are going to be antiports because they're moving in opposite directions. So those are antiports moving in opposite directions. So this will be our last one to draw out. I'm going to erase those two circles so they aren't confusing. But now we can use our arrows. We know that sodium is going to be moving in because we're trying to absorb it. And hydrogen is going to be moving out because we're trying to secrete it. And same thing on this side, sodium is going to be moving into the body because we're trying to absorb it. And hydrogen is going to be moving out because we're trying to secrete it. So one more time, or one last time, take a second to decide which one you think is correct, which side it should be in. And this is the last time I will tell you, the incorrect one is this one, because we want to secrete hydrogen. We want to get it out of the body. So this method would be keeping it in the body by keeping it in one of those epithelial cells. We want to fully secrete it out of the body and get it in that lumen to be excreted. So this is our final cell diagram. So with this, these next few questions will make a lot of sense. So let's go ahead and start knocking them out. So number 1A is talking about sodium absorbing epithelium, such as tubular epithelium is the ATPase on the which side? So which side is going to be dealing with that sodium sodium potassium ATPase transporter? Well, if we look back up at this diagram, we can see that that is going to be on the extracellular fluid side, and I'll color code this as well to follow up above. So we can see here, that's on that extracellular fluid side. That's that ATPase, sodium potassium transporter. Nice. So question B says, which membrane is the apical or apical membrane? Apical membrane is going to be the membrane on the luminal side. So that is the luminal side. Basal membrane would be the opposite. So the basal membrane would be on the extracellular fluid side. C is saying, on which membrane should you find the sodium hydrogen co-transporter? So we can again look back up at our diagram using our colors. We can see that that sodium hydrogen co-transporter is on this side. So we can see that that is on the luminal side as well. And then we move on to question D. This transporter is an antiporter or a symporter. Remember, antiporters move in opposite directions, symporters move in the same direction. So if we look up at this sodium hydrogen transporter, co-transporter, we can see it's moving in opposite directions, which means it's going to be that antiporter. Question E is saying, where would you expect to find the sodium channel? We can look back up at our diagram again and see that that sodium channel is going to be on that luminal side. And then our last question says, given that the sodium bicarbonate co-transporter is on the extracellular fluid membrane, do you think it is an antiporter or a symporter? So we can go back up and look at that sodium bicarbonate co-transporter right here. They're moving in the same direction, being absorbed by the body. So that means it is a symporter, a symporter. Question 2B says, based on the information above and your answer to 2A, which molecule is moving by secondary active transport? The answer for this one is going to be sodium. And we know that because of two things. We know that because of this example right here, we can see that we are using that secondary active transport to move sodium against its concentration gradient. So we're moving it from high to low, or from low to high against its concentration gradient, and we're getting energy to do that from bicarbonate. But we can also see that we are using secondary active transport to move that sodium molecule when we look at the sodium potassium ATPase, so the sodium potassium pump. Sodium is again moving from a low concentration to high concentration, and it's doing that by getting energy from potassium, secondary active transport. Again, secondary active transport means we're getting energy from another molecule, so we can move one molecule against its concentration gradient. So number 3, we're going to maybe hit in lecture, but we won't be hitting it in this discussion. So that is all I have for y'all. I hope you have a great weekend or week, depending on when you watch this, and I will see y'all for our first in-person discussion next week, or you can continue watching the recordings, whichever works best for you. Again, I don't take attendance. I won't be picking up any papers or doing any grading. So it is up to you whether you come in person or you just watch the recordings. So thank y'all so much, and bye.